In this video, we will explore the least recently used, or LRU approximation algorithms. These algorithms provide efficient ways to manage page replacements in operating systems. We will cover the clock algorithm, which is a second-chance algorithm with a circular queue implementation. We will also delve into algorithms that use additional reference bits for tracking the history of page usage, and counting algorithms that use counters to approximate LRU behavior. Let's dive into the clock algorithm, an efficient way to approximate the least recently used, or LRU, page replacement policy. Also known as the second-chance algorithm, it uses a circular list structure with a reference bit for each page frame. Imagine a clock face, where each position represents a page in memory. A hand moves around the clock checking each page. This algorithm uses a single reference bit per page frame and implements a circular queue with a pointer. It's significantly more efficient than true least recently used and requires minimal hardware support, needing only the ability to set reference bits. Here's how the clock algorithm works. When a page fault occurs, the algorithm examines the page where the clock hand is pointing. If the reference bit is 0, indicating the page hasn't been used recently, the algorithm replaces that page. However, if the reference bit is 1, meaning the page has been used recently, the algorithm gives it a second chance. It sets the reference bit to 0 and advances the clock hand to the next page. This process repeats until a page with a reference bit of 0 is found. If all pages have a reference bit of 1, the algorithm will reset all bits to 0 in the first cycle and replace the first page it encounters in the second cycle. Now, let us look at the pseudocode of the clock algorithm. While true, if pages at the clock hand's reference bit is 0, then a victim page is found and the new page replaces the victim page. The clock hand moves to the next page and returns the victim page. Otherwise, the page is given a second chance, where the reference bit is set to 0 and the clock hand moves to the next page. Let's walk through an example of how the clock algorithm operates. Consider a scenario where we need to load page 9 into memory, resulting in a page fault. Initially, we have 4 frames with pages 1, 2, 3, and 4. The clock hand points to page 3, which has a reference bit set to 1. Giving page 3 a second chance, we set its reference bit to 0 and advance the clock hand to page 4. Now, page 4 has a reference bit of 0, so we replace it with page 9, set its reference bit to 1, and advance the clock hand to the next position. For the next fault, it would point to page 1. The additional reference bits algorithm enhances the tracking of page usage by storing multiple reference bits for each page frame. Instead of just one reference bit, this algorithm uses, for example, an 8-bit register to track the history of page references. Periodically, let's say every 100 milliseconds, the register shifts to the right, and the current reference bit is added to the leftmost position. Higher register values indicate more recent usage. This provides a more accurate least recently used, or LRU, approximation compared to the basic clock algorithm, but requires more hardware support. Imagine we have 4 pages and their 8-bit history registers are given. The decimal values for each of the history registers can be used as an LRU rank. For the shifting mechanism, a new bit is inserted and the oldest bit is shifted. Let's illustrate how the additional reference bits algorithm tracks page usage over time. We'll observe the state of 2 pages, page A and page B, at different time intervals t0 through t4. At time t0, the initial state, page A has a certain bit register and value, and page B has a different bit register and value. As time progresses, every 100 milliseconds, the registers shift, and new reference bits are added. Notice how the values change over time, reflecting the page's usage. Now at time t4, if a page needs to be replaced, page B with a lower reference history value would be chosen over page A, indicating less recent usage. Now let us take a look at counting algorithms. Counting algorithms use counters to track page usage and make replacement decisions based on these values. The first algorithm is least frequently used, or LFU. This algorithm replaces the page with the smallest usage counter, incrementing the counter each time a page is referenced. It assumes that pages used frequently in the past will be used frequently in the future. The next algorithm is most frequently used, or MFU. This algorithm replaces the page with the largest usage counter. Its argument is that a page with a small count was probably just loaded and is still being used. And the final algorithm is not frequently used, or NFU. This algorithm combines reference bits with counters. At each clock interrupt, it adds the current reference bit to a counter and replaces the page with the lowest counter value. Let's look at an example. In this example, the LFU is simulated and a page reference sequence is executed. In the LFU, the page with the lowest counter value is replaced when a new page needs to be loaded. This can lead to problems with pages that were heavily used in the past but are no longer needed. Let's look at an example of the not frequently used, or NFU algorithm. NFU periodically samples the reference bit of each page and adds it to a counter. This creates a history of page usage that approximates least recently used, or LRU behavior. The page with the lowest counter value is selected for replacement. In this example, there are 3 steps with the page table. Each page table contains the pages, the counters, and the reference bits. If a page fault occurs after step 3, page 4 with a counter value of 3 would be selected for replacement. The NFU provides a better approximation of LRU than simple counting algorithms by considering both frequency and recency. Let's compare the least recently used, or LRU approximation algorithms we've discussed. The clock algorithm is simple to implement, requires only a reference bit for hardware support, and has low memory overhead and performance impact, but its accuracy to true least recently used, or LRU, is medium. Additional reference bits offer high accuracy and moderate implementation complexity, but they need a reference bit and timer for hardware support and have medium memory overhead and performance impact. NFU, or not frequently used, also has high accuracy and moderate complexity, needing a reference bit and counter with medium memory overhead and performance impact. Least frequently used, or LFU, is simple but has low accuracy, needing only a counter, and it has medium memory overhead and performance impact. All these algorithms trade off implementation complexity against accuracy in approximating true least recently used, or LRU behavior. The choice depends on hardware capabilities, performance requirements, and memory constraints. For example, the clock algorithm offers the best balance of simplicity and effectiveness for most systems. Additional reference bits provide a better approximation when hardware support is available, and counting algorithms can be problematic with changing access patterns, but work well in specific scenarios. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.